Yours.
Well, thank you very much for the kind introduction. My name is Henning Lategahn, and before I start the presentation, I will have to say one thing. This work that I'm presenting here has primarily been conducted by my colleague Bernd Kitt, who just got sick yesterday, so I'm the substitute presenting the work today. The subject of the presentation will be on visual odometry, and these are the steps that I would like to talk about. First, I would like to give a small motivation why one would be interested in using visual odometry in intelligent vehicle technologies. Then I will just sketch the processing chain that we use to achieve this goal. And then in the middle of the presentation, I will talk about the algorithm that we developed and go a little bit more into the details. And toward the end, I will show experimental results and finish with the conclusion and outlook. So many of advanced driver assistance systems rely on a precise perception of the vicinity of the vehicle, and basically all perception algorithms have one thing in common, and that is that they rely on a very precise ego motion estimation and also on the localization of the vehicle. And if this is possible, many of the things come possible, like self-localization, collision avoidance, and such things. So usually cars are equipped with wheel encoders, which can be used to estimate the motion of the vehicle already. So I would like to motivate the use of cameras in this setup also. First of all, cameras have been becoming more and more inexpensive over the past years, so they are just approaching in the car industry. They provide a very high bandwidth, both in spatial and temporal resolution, and they are not affected by the environment. So if the terrain that the car drives on is wet, let's say, then there may be some slipperage, and the wheel encoders may provide false information, and camera setup is not affected by the ground that the vehicle is driving on. And one last point that I would like to stress here is that if the image processing is also used for the environmental perception, then it is difficult sometimes to align the ego motion from an external sensor with the camera data, so like problems with timestamps and everything may occur. And if the vehicle ego motion is computed entirely from the camera, then there's no synchronization issues. This is an overview of the algorithm that we use. First of all, in the first step, all that is needed for the entire algorithm is just a stereo setup and a stereo image sequence. And at first, features are detected in these stereo camera images and matched. I will go into more detail just after the slide. And then once features are matched across the image, in a second step, a bucketing scheme is applied to reduce computational complexity on the one hand, and also to reduce the drift rate on the other hand. And finally, this is really the core of our algorithm. We have applied a Bayesian filtering to estimate the motion, and this is implemented by an iterated sigma point Kalman filter. So I will go over all these three steps in more detail now. Well, first of all, observe this camera setup here at the top. These are the cameras that are mounted on the vehicle, which move over time. So this is one time step, let's say time step k, and it has moved over time to time step k plus 1, and it's positioned here. And what we seek is an estimate of the 6 degrees of freedom ego motion between these two consecutive views. So here at the bottom, you can see these two camera images, these two stereo frames captured at these two time frames. So this is the stereo image pair that is recorded here, and this is the next camera stereo camera frame that is captured here. And the first step consists of detecting features in all of these four images. So if this is a current image and this is a previous image, then a feature detector is run on all these images, and there are a variety of different image interest point detectors, something like SURF or SIFT or Harris, and there are many more. For our experiments, we have so far used the U-surf detector, and this is just an example of these features that are detected. Now, the second step that is required by our algorithm is to match features across all 4 images. So after the matching process, this may look something like this. So we have correspondences for each such point in the stereo frame and also temporally. So we match each frame, each feature in a circular manner here. And we have already applied some robustness to this step so that as first, a match needs to be unique. So we compare the best matching score to the second best matching score, and there has to be some improvements to the second best matching score. And if there's some ambiguity, we will just neglect that match. And also, once we have matched in this circle, we require that the last match matches the very first point. So if there's no closure, then we also do not use that feature match. And one last comment on this slide, the stereo camera rig does not need to be rectified. So this works with a general camera setup. We have found experimental findings that if we distribute these features uniformly over the entire image, that this reduces the drift in the estimation and that it increases accuracy and also reduces the computational complexity if we don't use too many features. To assure both of these points, we have used a bucketing scheme, which simply means that we partition the image into non-overlapping regions like it is depicted here, and for each such bucket we only allow a certain maximum number of features to used in the upcoming processing steps, and you can see that we have just thrown out these blue points here and have retained only the red ones. And as I said, this also, of course, reduces computational complexity if not all the points that have been found are used. The estimation that we apply to derive at the motion estimate is using the trifocal tensor. So I will just very shortly introduce the trifocal tensor. The trifocal tensor is denoted by this T here, and it encodes the information of 3 different cameras and their spatial arrangement and also their intrinsic camera parameters. So KA here and BC are the camera parameters which encode the intrinsic parameters of all these 3 cameras, and R and T are rotation and rotation matrices and translation vectors which relate the view of these cameras to some coordinate system OW, denoted by OW. And all this information here is packed into the trifocal tensor, which can be computed by this formula right here. So the important point here is that the rotation between these 3 camera views is somehow encoded in the trifocal tensor. So for our application to estimate the echo motion, we need this following equation right here, which says that if one point in the world is projected into these 3 camera images, and we have found these pixel positions in 2 of the cameras already, say XA and XB, and we do know the trifocal tensor, then we can estimate or predict the pixel position of that very point in the third view. So if we know XA, XB, and the trifocal tensor, then we do know where this point is in the third image. And this transform, so to transform the point correspondence into the position of that point in the third view is called point-line point transfer. This is very similar to the previous slide. We have these stereo camera set up just like at the beginning, and we have the current stereo camera and the previous stereo camera, and the relation between these 2 cameras is the rotation matrix RR and TR, which is a translation vector, and the relation between the 2 stereo cameras is encoded by this rotation matrix C and RC and translation vector TC. And you can see that these 3 cameras also, or the information about these three cameras can be used to construct the trifocal tensor. So if the camera matrices are known and if these rotation and translation vectors are known, one could construct a trifocal tensor for this image, and this image. And the rotation that is encoded in this trifocal tensor is precisely what we are actually looking for. This is the ego motion that we're trying to estimate. And the motion is, in our case, parameterized by this translation vector here and the rotation vector by these three angles. So again, this is a 6 degrees of freedom ego motion estimation. To estimate the ego motion now from the setup, we have put the quantity of interest, which is the ego motion, the linear and angular velocities into one vector, which we denote by y, and this is a result of our estimation. So this is what we are interested in, and to apply a Kalman filter, we need to specify two things. First, we need the system equation and the measurement equation. The system equation is quite simple. We assume a constant velocity, so the vector doesn't change during prediction. And the important point now, and this is really the crucial part, is that measurement equation can be used via the trifocal tensor to predict the position of the features. Now, if this is known and the time between the two stereo camera frames is also known, the rotation matrix and the translation vector can be computed between these two camera frames. And since we already know the rotation matrix and the translation vector between the two single stereo cameras, one can construct the trifocal tensor as it was mentioned on the previous slide. And with that measurement equation, now since we have correspondences in the current frame, so we have feature correspondences in the current frame, and we take these for granted, and we have these the belief in the current velocity, we can predict the position of these feature vectors in the upcoming stereo frame. And this is our measurement equation. So we predict the position of these features in the next stereo camera frame. And that can be solved then by an iterated sigma point Kalman filter. And just on the next slide, I will also justify the choice for the iterated sigma point Kalman filter as opposed to the iterated extended Kalman filter. And this is the slide. What you can see here is the termination threshold that is used during iteration. So this is the largest amount of change in the parameters that is still allowed to continue with the computation. So if it drops below, the iteration is terminated. And here you can see the number of iterations comparing the iterated sigma point Kalman filter, which you can see here in blue, and the iterated extended Kalman filter, which you can see here in dark red. And you can clearly see that the iterated extended Kalman filters needs 1 magnitude or 2 magnitudes more in number of iterations to converge. So one last problem to be resolved remains, and that is that these matches that we have initially computed are subject to outliers. Outliers may come from two sources. First, of course, there could be false matches, even though we try to mitigate that problem already at the beginning. One can never be sure to have perfect matches, of course. And the more important part is that these outliers may also originate from, from dynamic objects which move independently. And feature matches on independently moving objects cannot be used for estimating its own ego motion, of course. So to address this problem, we have applied a RANSAC scheme. So first, we take only 3 matches, which is the minimum number of matches required for this filter to converge to a solution. Then we run the entire iterated sigma point Kalman filter machinery to derive at an ego motion estimate. And then we score all the matches that we have initially computed as inlier or outliers. And then we repeat this several steps and take 3 new matches and continue and do the same thing again. And at the end, we at the end, we choose the maximum number of inliers and run the entire estimation process again. And this is the end of the iteration, and this is then the current estimate of the ego vehicle's motion. Before I come to the experimental results, I would like to briefly explain our testing vehicle. So this is a testing vehicle. It is equipped with a stereo camera rig here on the roof. We also have an active stereo camera rig, which is not used for these experiments, but in general they could be used in the future also. Of course, we have an INS, which we use just for reference, that we have something to compare our estimate to. And here are just some information about the stereo camera rig that you can see up here. And the very first experiment that we have conducted can be seen here on the left-hand side. This is simulation results, so this is not this is not real-world data. This is a simulation, and we have investigated the performance of the RANSAC scheme and whether or not this is necessary or not. And one can clearly see that it is necessary. In red, you can see the ground truth that we have used for this simulation. Blue is the estimated trajectory with the RANSAC scheme, and green without. So without outlier rejection, the estimation process is not possible. Here on the right-hand side, this is real-world data. You can see a top view of the trajectory. Colors encode the same thing. So red is the INS sensor, which we use for reference, and blue is the estimated trajectory. You can also see this in a video, which is coming on the next slide. The top is the input to the algorithm. Only one frame is depicted here. And at the bottom, you can see the current estimate in blue and vehicle orientation compared to the INS sensor displayed in red. And this sequence is rather challenging because the vehicle stops and drives forward and backward and turns around a lot. And we can see at the end of the sequence that the result is quite good and that the drift is not severe. So it's continuing now on the street, and the blue and the red lines align very, very nicely. The next sequence, I can show you also experimental results. The proposed algorithm is used to estimate the motion. This is the input sequence, accelerated. And we have also run dense stereo on that image sequence, and we have integrated our motion estimate to derive at a global position estimate, and each reconstructed stereo frame is registered to that global position estimate. And one thing I would like to stress here is that since this is a 6 degrees of freedom ego motion estimation, one can really clearly see that the bridge that we have gone under first and then over can clearly be seen here in this reconstruction. And I will just show this again, that you can look at the bridge, please. So first it's gone under the bridge, and after a few turns it's going over the bridge. And here you can clearly see that in the reconstruction. So please note here that you can also see the bridge in the reconstruction. And here, of course, the ego motion is entirely estimated from the image sequence. So to summarize, the algorithm, a robust visual odometry algorithm, was presented using only stereo cameras. The algorithm provides accurate local motion estimates, and if these local motion estimates are integrated over time, you may also obtain a global position, of course, that drifts. Then almost arbitrary camera configurations are possible for this, so there's no rectification necessary because it works basically on the trifocal tensor, and the ego motion estimation runs in real time. And we are also planning to put the source code for these ego motion estimator on the net. You can visit this website, cvlips.net, and it will be there available. It is not there yet, but it will be there very shortly. outlook. One thing that could still improve the performance is to classify each interest point that is detected in the very first step into two classes, which are potentially moving objects or potentially stationary objects, that from the visual appearance already, some points can be neglected or ignored, and then to speed up the entire process, and also that fewer RANSAC iterations are needed to achieve the same robustness. And this has been done by my colleagues Bernd Kitt and Frank Moosmann. They have done this, and here's the classification result. Blue points are potentially moving objects, and red points are potentially stationary objects. And well, this improves the accuracy, and this is being published at IROS this year. Okay, so thank you very much for your attention, and if you have questions, I'll be happy to answer.
Yes, thank you very much. Very impressive.